Yes, my name is Thomas Gernay, and this presentation is about the behavior and design of concrete structures under natural fires. So what I'm going to present comes from a project that was supported by the ACI Foundation and also by ACI 216 for fire design. I want to acknowledge the advisory panel. So the members are listed here who provide great inputs and support through the project. So this research is part of a broader effort to develop performance-based structural fire design in line with what Kevin just presented. And in particular here, we are interested in understanding what happens during the cooling down phase of a fire, because once you are moving from the paradigm of looking at standard fire exposure and just continuously heating our member until failure, and instead we are using structural design fires, which represents the expected, anticipated real conditions in the building, we are always going to have a heating phase followed by a cooling phase. So we want to understand what those cooling phases do and what is the impact on the structures, establish an analysis procedure to evaluate whether concrete members would survive to full burnout, so remain stable throughout the entire fire, including the cooling phase, and look at current simple design provisions, including tabulated data in ACI 216, against, again, this burnout resistance criteria, and whether designs according to those tables would provide resistance to full burnout, and if not, how this could be amended. So why caring about the response during the cooling phase? Well, I just touched upon briefly, but really this is a new need arising from the emergence of structural fire engineering, because real fires include cooling phase. Most specifically in the performance-based structural fire design, the first step is to define performance objectives for the design. So that's again a change in paradigm. We're not just taking a deemed to satisfy solution, but we are talking with the stakeholders, the building owners, in defining what is the desirable performance of the structure. And we can have different types of performance objectives, including survive to full burnout or even being reused after a fire, and some resilience objectives. At the same time, we recognize that failure during cooling can happen. That's true for any type of building materials, primarily because of delayed heat transfer. There are other effects, strain reversals, further degradation of strength, etc. But primarily, once the heating stops, the inside of the sections, the core of the structure will still continue heating for a while, and so the load-bearing capacity continues to decrease. And we've observed in real fire some structural collapse during the cooling phase. So what do we need for this assessment of the behavior during cooling? First of all, we need to start collecting data on the properties during the cooling phase. So for a long time, we focused on elevated temperature properties, but now we want to know also the residual properties after cooling. Well, this has already been done to a certain extent, but also the properties during the cooling phase. This we don't really have data for that. So we need new experimental protocols, and we need then material models and provisions that we can use in our numerical simulations. We need data on the response of members during the cooling phase, so we can use simulations when we have the material data to model the structural response throughout the fire exposure. And with that, we can collect data on burnout resistance, which I'm going to define in a moment, and then look at simple methods or pre-designed tables that would give provisions for addressing the vulnerability to the cooling phase for achieving burnout resistance. So in the first phase, we started with the experiments and collecting those material properties. We looked at different concrete mixes. We designed two types of tests. So the first types focused on the thermal properties. We wanted to measure thermal diffusivity during heating and cooling. And then we also looked at compressive strengths. So for the thermal test, we looked at measurements of temperature in concrete cylinders. So by measuring the temperature at two locations inside the specimens, and looking at the conduction problem there with axis symmetry, we could derive the thermal diffusivity. And again, what was important here was to monitor closely what was happening not only during heating, but also during cooling. So the thermal diffusivity is a material property that includes conductivity, specific heat, and density, and is the key driver of conduction in the material. So this plot shows the outcome of those thermal diffusivity measurements. On the left part of the plot here, so all this part, it's the heating phase, okay, up to this vertical bar. And so you can see those curves relate to different specimens, okay? So we measure the thermal diffusivity continuously during heating. And then here on the right-hand side, you have the results when we return back to ambient temperature. So a couple of things that we can see here. So we have those big peaks, okay? Here it's linked to moisture effects, okay, around 100 degrees C, and here it's the effect of quartz. So these are already known. And in heating, you have provisions in standards, notably in the Eurocode here, there are two curves that bound the behavior. And so we see that the trend followed basically these laws. It's not exactly with some variability, but overall, what is in the standard captures the variation of thermal properties during heating. However, what was new was this right side of the plot, and what we found was that the thermal diffusivity was irreversible. Okay, so we didn't have the same type of variation during cooling that we had in heating. Basically, the curves are almost horizontal. So it means that those thermal properties, they are not recovered. They keep the values that they had at the maximum reached temperature. So that's important in simulations. If you want to capture the continued heat transfer during cooling, part of the section at the periphery will be cooling, and we have to use the right thermal conductivity and so on. So next experiments dealt with compression tests, compression strengths. So here, the test protocol that we devised, it included defining two important temperatures for concrete cylinders. The temperature Tmax is the maximum temperature that we will reach during the heating of the specimen. And then the temperature T-test is the temperature at which the test is performed. So if you look at, for example, the column at the right here in this table, this means that we'll take concrete cylinders, we will heat them to 600 degrees C. Some of them, we will test them at 600 degrees C, so that's the elevated temperature measurements as is usually done. But then others, we will heat to 600 degrees C, wait for a while, cool down to 400 degrees C, wait for the temperature to stabilize, and test at 400 degrees C. We do the same at 200 and at 20, and 20 is the residual strength measurement. So that we track the loss of strength during cooling and the residual value. These results show the measurements for the residual test. So these are the tests when we heat it up to a certain temperature Tmax, and then we cool down all the way to 20 degrees C, and we tested the residual value. So we had different mix, and I'm not going to go into the details, but what's very important here is that the residual strength is below the curve, the provisions for the hot value, for the elevated temperature strength. Okay, so you see here for different mix, we are always below this hot curve. It means that there is additional degradation of strength during the cooling back to ambient temperature. This was already known largely, and actually in the next version of Eurocode, the PREN 1992 that you see here, they will have a curve for residual strength which is lower than the hot curve. But so that's also what we found in our experiments. These are the hot values, so just the measurements at elevated temperature. So here, nothing new, and we found that the provisions in the codes are mostly conservative or appropriate. But most interestingly, these are the intermediate measurements during cooling. So here, if we focus, for example, on these set of data, okay, you see on the horizontal axis is the temperature of the test. And all those dots, those void circles, they refer to specimens that were heated to a maximum temperature of 600 degrees C, okay? So these measurements are the hot measurements at 600 degrees C, and then we are cooling and measuring at 400, 220. So you see again that the residual strength at 20 is lower than the hot value. That's true for all specimens. But you see that the trend while cooling is not really consistent, or we couldn't find any real logical trend there between the different mixes. So we always had further degradation of strength, but it was not a linear process. So on the experimental program, really the main takeaway is that the thermal properties in the heating phase, we are fine with code provisions, but in the cooling phase, we should consider they are irreversible. So if you do a numerical simulation, you should keep the value at the maximum reached temperature, not at the current temperature while cooling. And for compressive strength, the residual value is lower than the elevated temperature value. We have additional strength degradation during cooling. And we believe for the first time we had measurements during the cooling phase at different intermediate temperatures. And I would say more research is needed to understand really what was going on. We didn't find a really consistent trend. Okay, so moving on, next we wanted to simulate entire concrete members during heating and cooling. And the way we framed the question was to determine what we call the burnout resistance. So here is what we wanted to do. If you consider a reinforced concrete column in a furnace, traditionally we heat it up to a certain time when it fails, and that's what we call the standard fire resistance. The question we want to look at is, should we stop the heating earlier, but keep the load applied on this column? Okay, but we stop, you see, at a time that's earlier than standard fire resistance, and then there is a cooling phase. Would the column survive or would it fail? And what we want to do is to repeat this analysis for different values of DHP, of duration of heating phase, and differentiate between the fires that lead to failure and the ones that are survived. So to do that systematically, we adopted what we call a standard natural fire exposure. So that's not the full performance-based design where each fire depends on each compartment, taking into account the fuel, etc. Here we want something systematic, so we heat always with the same curve, time temperature curve, and then we have a linear cooling phase. And so by subjecting different members always to this type of standard time temperature curve, but with a cooling phase, we can benchmark and compare the vulnerability to the cooling phase. We applied this numerical method to different types of concrete members, so columns, walls, beams, and slabs. So that was all in the context of this research project. I'm not going to go into the details for all, but to show you an example for concrete columns. So what is key really is that we modeled this concrete column with the finite element method, and we subject it to heating followed by cooling, and we study different duration of the heating phase. And what we call DHP is the shortest duration of heating phase that results in a failure. So it's basically the threshold of thermal exposure that the column has been subjected to so much thermal exposure that it will fail eventually. And what we found, so again, because of this delayed heat transfer, when you enter into the cooling phase, you have the core of the section that continues heating, even though the perimeter starts cooling. And so what we found is that there is approximately a linear relationship between the burnout resistance and the fire resistance. In other words, if you have a concrete column which has a 90 minutes fire resistance, it would fail eventually if you expose it for the heating phase for more than 63 minutes or more. So this kind of gave us a framework to systematically quantify the vulnerability to cooling and differentiate between those fires that result in failure eventually and those that are survived. So we did lots of simulations varying the cooling phase and so on, and looking at those different members. I'm going to skip that, but again, conceptually, what we want is to divide the time domain in 3 zones. Everything that's shorter than DHP, of course, this is for standard natural fire, but everything that's shorter is going to be survived indefinitely. If the exposure to this particular standard fire lasts for more than DHP, the member is being exposed to so much heat that it will eventually fail. And then once we reach standard fire resistance with this particular exposure, it has failed. So as the last part of the project, we looked at the current tabulated data in ACI 216, and we looked at what it would mean if we had to adjust those provisions for thickness, for cover, to make the members survive to full burnout, and not only for specific fire resistance time. So as an example here for the thermal insulation criteria of concrete floors, you have a table that gives minimum thickness in ACI for different duration of standard fire rating. So we can model those floors in a finite element model. Now we have the material properties owing to the experimental task that I've shown. And we can look at how the temperature on the unexposed phase continues to increase for a while during the cooling phase, and then eventually cools down. And so by repeating these analyses for different thickness of the floor, we can find the minimum thickness such that this maximum does not exceed a limiting temperature. For example, we can relate it to the values in ASTM E119. And so we could, with that, we can adjust the tables and give the thicknesses to achieve the same limiting criteria, but now including during the cooling phase. So we can do the same for cover, looking at stability of members, and we have done that also a provided table. So I'm going to go fast on this, but we have published the report now because the project has been completed. So I want to relate that to the performance-based fire design, which is the topic of this session. There are some aspects of the project that are directly related, and somewhere we went more toward the prescriptive to make it also very, I would say, practical and to raise awareness to the effects of cooling phase. But the first step in a performance-based design is to determine the performance objectives, as I said. And so in many cases that will entail explicitly evaluating the response throughout the fire, including cooling. So we believe notably the properties, thermal and mechanical properties that we provide in this project are going to be very helpful to do that. The second step is to determine design fires. So in this project, I want to make clear that we did not work with specific fire that would occur in one given compartment, modeling the fuel and ventilation and so on. That was not the objective. On the contrary, to try to have a systematic approach and allow comparison between members, we adopted this standard natural fire, which is a little bit in between, well, the standard ASTM E119 fire and performance-based, because we do have the cooling phase. But this is not really not a full performance-based design in that sense. But then what's interesting as well is that we show the procedure to quantify the response of structural members, concrete structural members, during the different phases of the fire, and notably to quantify burnout resistance, and that can be adopted with any design fire. So in conclusion, we have shown new properties during cooling. Thermal properties should be considered irreversible, and compressive strength further degrades during cooling compared to the hot value. We have showed a systematic procedure to assess the resistance to full burnout of different concrete members. And it's important to remember, probably the most important thing to remember is that any type of structural member is vulnerable to failure during cooling, so any material, any type of member. And so we can quantify the burnout resistance, which is going to be shorter than the fire resistance. The time of failure is going to be later, but the duration of exposure to a fire is going to be shorter. Thank you for your attention, and if you have any questions, I'll be happy to take them.
We do have a question in the Zoom, and it says, I was wondering if the cylinders were loaded before exposing to temperature.
Can you say that again?
The question is, I was wondering if the cylinders were loaded before exposing to temperature.
Were loaded before exposure to temperature?
Yeah.
No.
No, they were not. Okay.
Yes. Yeah.
So,
So with all of these tests, were you accounting for or recording the moisture condition for the cylinders and the oven testing, but also in the full scale testing? Were you detailed in the moisture content, values for those? And if so, how did you quantify them? How are you reporting them?
Yes, thank you. So about the testing of the concrete cylinders, so they were, that was following the procedure specified by the RELAM in terms of storage condition and monitoring of the moisture during the storage for certain duration. So I don't recall exactly the condition, but yeah, that was done for, there is first 7 days at certain moisture condition in the room, and then for 3 months, other conditions and so on, yes. But is your question during the heating, if the moisture was monitored during heating?
No, I'm saying before heat application. So, within a few hours before you started
Yes.
fire testing, were you taking moisture content measurements from the surface of your specimens,
Yes.
checking the relative humidity, and are those quantified in somewhere that we could get a hold of them?
Yes. I can't tell you by heart the value, but yes, that's in the report, and that was done. These tests were done at Polytechnic Milan. Yeah.
what type of analysis program do you use for defining
So yes. So the question is, what type of finite element software was used? So that is the finite element software Sapphire, which is a program specially designed for structural fire analysis. So it does thermal and structural analysis. Right. Thank you very much.